Welcome to The Explainer. So, if you're a graduate student working with things like batteries or fuel cells, you know that feeling. You're staring at your experiment and it basically feels like a black box. Well, today we're going to crack that box open by demystifying a really powerful technique, electrochemical impedance spectroscopy.
Okay, let's start with something we all remember from Physics 101, right? Ohm's law. V equals I times R. It's simple, it's reliable, it's kind of the foundation for how we think about electricity. But what happens when things get a little more messy?
And that's the big question, isn't it? When you're looking at a real system, your battery, your corrosion experiment, whatever it is, that simple little R for resistance, it just doesn't tell the whole story. The opposition to current in there is way more complex than just simple friction.
So, to actually get what's going on, we have to expand that idea of resistance. We need a concept that's more comprehensive, something that captures the full picture of all the action happening at, say, an electrode surface. Think about classic resistance, what we call the real part. It's super straightforward. It's just an immediate opposition, and it turns electrical energy into heat, like friction. The key thing is that the current and voltage are perfectly in sync. They're in phase. Okay, but here's where it gets really interesting, especially for electrochemistry. The systems you're studying, particularly that crucial interface between the electrode and the electrolyte, they don't just dissipate energy. They also store it for a little bit, kind of like a tiny capacitor. And we call this energy storing part reactance. So if resistance is like friction, the best analogy for reactance is pushing a kid on a swing. You give a push, but the swing's response is delayed, right? It's out of sync. That delay, that out-of-phase response, is everything. The system is storing and then releasing energy. So you take the friction part, the resistance, and you add the energy-storing swing-set part, the reactance. Put them together, and voila, you get the total opposition. We call that impedance, and we use the letter Z to represent it. That's the whole shebang. So, how on earth do you mathematically handle two totally different kinds of opposition at the same time? One that's instant and one that's delayed? Well, for that, we need to pull out a more powerful kind of math. We need the language of complex numbers. See, a single number just won't cut it anymore. It's kind of like trying to find a spot on a map with just one coordinate. You can't do it. You need two dimensions, one for the energy dissipating resistance and a second one for the energy storing reactance. And this is where complex numbers are just perfect for the job. We can map the resistive part, which we call Z prime, on the real, or x-axis, and we map the reactive part, Z double prime, on the imaginary, or y-axis. And it all boils down to this really elegant little equation. The total impedance, Z, is just its real part, Z prime, plus its imaginary part, Z double prime. That's it. That's the mathematical heart of this whole thing. All right, the math is cool, but pictures are usually better, right? So let's see what this actually looks like. We're going to map this impedance out on a special kind of graph called a Nyquist plot. Let's start simple. Look at plot A. This is a pure resistor. It has only a real component. No energy storage at all. So where does it show up on our plot? Bam, just a single dot right there on the real axis. And no matter what AC frequency you throw at it, that dot does not move. Now, check out plot B. This is a perfect capacitor. It's the complete opposite. It only stores energy, so its Nyquist plot is a straight vertical line right along the imaginary axis. And for this guy, the opposition it presents is totally dependent on the frequency you're using. And now, this is where the magic happens. Look at plot D. When you combine a resistor and a capacitor, you get this beautiful semicircle. This shape, this is what you're looking for in the lab. It's the classic signature for many electrochemical processes. Each point on that curve is the total impedance at one specific frequency. This is the power of the Nyquist plot, turning complicated behavior into a shape you can actually recognize. Okay, we've got this great visual tool now, but let's zoom out for a second and think about what impedance really is. It's not just some property. It's a description of how your system behaves. It's what engineers call a transfer function. Now, transfer function sounds way more complicated than it is, I promise. All it means is you put a signal in, your system does something to it, and it spits a different signal out. The transfer function just describes what happened in the middle. And that is literally what you're doing in an EIS experiment. Step 1, you apply a small known AC voltage. That's your input. Step 2, that signal goes through your electrochemical cell. That's your system. And step 3, You measure the current that comes out. And guess what? It's changed. Its size is different, and it's out of sync with what you put in. So, simply put, impedance is the transfer function for this situation. It's the specific recipe that tells you exactly how your electrochemical system turns an input voltage into an output current. It's the complete description of that change. Okay, deep breath. We've gone through resistance, reactance, complex numbers, the whole deal. But let's bring it back to the lab bench. Why does any of this matter for your experiment? How does this actually help you figure out what's going on in that beaker? The ultimate power of EIS, the whole reason we do it, is translation. You're taking a real, messy, complex physical system, like the one on the left, and you're modeling it as an equivalent electrical circuit that behaves in the exact same way. This is so cool. It lets you take a chaotic chemical reaction and represent it with clean, simple electrical parts. You analyze your Nyquist plot, you measure the values of those resistors and capacitors in your model, and those values mean something real. That resistor might represent charge transfer resistance. It tells you exactly how fast your reaction is. You're no longer guessing. You're quantifying what's limiting your system. But here's the really clever part. Different things inside your cell happen at different speeds, right? Well, EIS can actually separate them. Fast things, like solution resistance, show up at high frequencies on your plot. Slower, more sluggish things, like diffusion, show up at low frequencies. This is huge. It lets you pinpoint the bottleneck. It helps you finally answer, what's the one thing that's slowing my whole system down?
So, by translating chemistry into the language of impedance, you really are transforming that black box into a source of rich, quantitative data. Which leaves us with one final big question. With this tool in your hands, what hidden processes in your own research could you now uncover?